Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exams. Of course, moving on, still on the theme gas laws, we'll be looking at ideal gas equation, looking at real gases, and how it deviates from ideal gases, and of course, looking at what we call Van der Waal equation and calculations related to ideal gas equation. So when we say ideal gas, you need to understand that an ideal gas is a hypothetical gas. Emphasis on the word hypothetical, which means it's just out of reasoning, it's just out of intelligent work, not necessarily that it has been proven. So an ideal gas is a hypothetical gas whose pressure, volume, and temperature behavior is completely described by the ideal gas equation. Now, talking about the ideal gas equation, what do we mean? You recall that we've said that for Boyle's law, volume is inversely proportional to the pressure. For Charles's law, we've said volume is directly proportional to temperature. And for Avogadro's law, we've said volume is directly proportional to the number of moles of gas. That's the amount of the gas. Now, combining these three, what it means is volume is that inversely proportional to pressure, volume is directly proportional to the temperature, and volume is directly proportional to the amount of gas. So that what this means is V equals to NT over P, and this will lead to a proportionality constant we call R here. V equals to what? RNT over P. Arranging this, okay, P coming here, PV. Arranging this letter alphabetically, this will mean nRT. You see, PV equals to nRT is our ideal gas equation. Ideal gas equation, PV equals to nRT. Your pressure is going to be in atmosphere here. Your volume is in liters, which is the same thing as saying dm cube. And your N here is the number of mole of substance. And your T is going to be in Kelvin. Talking about your R, that's our universal gas constant, with a figure of 0.082 atmosphere liters per Kelvin, atmosphere liter per Kelvin per mole. So that is a constant. With this, we actually can deal with questions related to the ideal gas equation. Okay, let's take one or two questions that relates to ideal gas equation. Like the first question states, what is the amount of gas in mole of a gas which occupies 5 dm cube at 3 atmosphere and 15 degrees Celsius? Looking at question 1 there, it says we should look for the amount in mole. Since PV equals to nRT, then I'm looking for number of moles, then N is going to be PV over RT. In this case, my pressure has to be in atmosphere. This is 3 in atmosphere. My volume has to be in dm cube, which is the same thing as liter. This is 5 dm cube. You can see that here, 5 dm cube, of course. And the temperature is 15 degrees Celsius. Our temperature must always be in Kelvin. So 15 plus 273, that's going to mean 288 Kelvin. And of course, our universal gas constant, that's 0.082 times this. So this is what we need to compute to get the number of moles of the gas here. So computing this, the answer here is 0.64 mole. That ends question 1. You look at question 2. We're told to calculate the volume. So the fact that we're told to calculate the volume, it means volume will be the subject. Volume here equals to nRT. Our P is going to come under here over P. So V here equals to the number of moles of the gas is 1.5. times 0.082. The temperature here, this is 10 degrees Celsius, must be in Kelvin. So therefore, this is 283 Kelvin divided by the pressure. The pressure is 2 atmosphere. This way, we're going to get the volume of our gas in dm cube or liters. Here we have 17.4 liters or dm cube. So that is that talking about ideal gas equation. It is a hypothetical gas whose pressure, volume, and temperature behavior is completely described by the ideal gas equation. So that is that about ideal gas equation. Now looking at ideal gases more closely, when we say ideal gas, an ideal gas does not accurately describe real gases because we have ideal gas. Remember that we had said that ideal gas is hypothetical, more of a gas, that we're talking about it on paper hypothetically, not as though it has been proven. So an ideal gas does not always accurately describe real gases. In fact, real gases deviate from ideal gases in terms of behavior. So we're still going to look at that deviation, how ideal gases and real gases deviate. But the thing is this: ideal gas do not always accurately describe how a real gas will behave. And when you talk about an ideal gas is any gas which obeys all the postulates of the kinetic molecular theory of gases. What are the postulates of the kinetic theory of gases, otherwise known as kinetic molecular theory? And that's exactly what we have here. The kinetic molecular theory states that gas molecules are in continuous random motion. That is, gases are in constant motion, always moving, randomly. They are not held together by strong cohesive force. You understand? The force therein is negligible, it is weak. Therefore, gases are in continuous random motion. That's the first one. The second one states that the volume of the gas molecules is negligible. Now, when you look at the fact that what we discussed under kinetic theory of gases before, when you talk about gases, the intermolecular force there, the force holding the molecules or the particles together is negligible. In fact, so in some cases we say non-existent or negligible. So if there are no binding force, if there are no intermolecular forces holding the particles together, it means the particles are free to move into any space accessible or available to them. So when you compare the volume of gases, that is why we say volume of gases is they have no definite shape, no definite volume. You can't tell their volume because they just move into any space. So when you look at the real volume of gases compared to the total volume of the containing vessel or the space accessible to them, you find out that the volume of gases is negligible compared to the total volume in which the gases contain. Because why? The particles are free to move in any direction, giving the appearance that they occupy the whole available space to them. So when you look their volume compared to the space the molecules are diffused into, we say the volume of the gas molecule is negligible. Also, attractive and repulsive forces between gas molecules are negligible. There are non-existent force holding the particles or binding the particles together. That is why the particles are free to randomly move into any space available to them. Also, collision of the gas molecules are perfectly elastic. That is, when the gas molecules collide with one another, they just bounce off each other without any loss of momentum. That is, energy can be transferred between molecules during collisions, but the average kinetic energy of the molecules does not change with time. So it means it is perfectly elastic. There is no loss of momentum here when the molecules of gases collide or bombard one another. Also, average kinetic energy of the molecules is proportional to the absolute temperature. The more the temperature here, the more the speed, the more the energy with which the molecules move. The lower the temperature, the lower the movement of the gas molecules there. So we say average kinetic energy of the molecule is proportional to the absolute temperature. This here is the kinetic molecular theory. And when we talk about ideal gas, it is any gas which obeys all of the postulates of the kinetic molecular theory of gases. Also worthy to note that for an ideal gas obeys the equation PV equals to nRT, and it also obeys the gas laws over all ranges of temperature and pressure. That's talking about the ideal gas. Now, the question is, how does ideal gas deviate from real gases? So, what are the deviations of real gases from ideal behavior? The first thing is, where real gases have negligible volume, we say they don't have a definite volume. For real gases, they occupy space and we can tell their volume. And also for ideal gases, we say there is no molecular attraction, there is no intermolecular force of attraction between the molecules, but for real gases, they are held together by intermolecular forces. These two here are the main deviations of real gases from ideal gas, and these two will lead to what we call our Van der Waal equation, because we are going to try to make correction to the volume to show that molecules of real gases, they have a definite volume, and also to show we are going to make correction to pressure to show that there is intermolecular attraction between molecules of gases. Also, real gases, we need to know they do not obey the ideal gas equation PV equals to nRT. If we make n the subject, it means PV over RT. Normally, you recall that when we plot Boyle's law, we say PV, and then we have our pressure as is here. When for ideal gas equation, when we plot, we're going to get a line parallel to the pressure as is. But for real gases like carbon dioxide, like hydrogen, like nitrogen, we are not going to get a parallel line. They behave in a real way. They do not obey the ideal gas equation when we plot the graph. For ideal gas, they will obey this equation, but for real gas, they do not obey this equation. For ideal gas, when you plot a graph of the product of the pressure and volume as against the pressure as is, you're going to get a line parallel to it. That's ideally. This is for ideal gas. But for your real gases, it is not the same. They are going to deviate from the ideal gases. Real gases will deviate from the ideal gases. But we need to also take note, there is a UTME questions. When you talk about real gases will behave ideally. Real gases behave ideally, like they imitate ideal gases when the temperature is high, at high temperature and at low pressure. At high temperature and low pressure, the gases move chaotically. They move so randomly, not in an ordered manner. And when they move without pattern, when they move just randomly, then it simply means truly there will be no intermolecular forces between them, and also they tend to occupy the whole available space to them. So when we talk about real gases at conditions of high temperature and low pressure, even real gases begin to imitate ideal gases. Let's quickly look at Van der Waal equations and some corrections to it. At least at this level, we really do not need to move in that deep, but let's gloss over Van der Waal equation. You know that for ideal gases, we have PV equals to nRT at this point, which means pressure is actually nRT over V. This is the normal ideal gas equation. Of course, Van der Waal made some adjustments here so that, okay, since the volume for ideal gas, is negligible in that it occupies the whole, accessible or available space to it, there has to be adjustment to volume. So, according to Van der Waal equation, pressure equals to nRT. Okay, there was an adjustment to volume using B. This here is the what we call correction for volume, so that if we reduce the space between the gases, then we can begin to talk of the volume of the gases not being negligible. This is the first adjustment here. Also, talking about correction for molecular attraction, recall that ideal gases have no molecular attraction. So, how do we make correction for molecular attraction? And of course, the next thing is to, reduce the pressure, so that when we reduce the pressure, there is what we call molecular attraction, and that is done m square A over V square. These A and B, A and B here. A and B are the two constants introduced by Van der Waal to make correction. So this here is the correction. This here is the correction for molecular attraction. Is the correction for molecular attraction, and what we have here is simply what we call our Van der Waal equation. We talk about correction for volume here by subtracting the term NB from V, and of course, correction for molecular attraction by subtracting N square A over V square from the pressure, and that ends our Van der Waal equation. Think about it again. Ideal gases have negligible volume, have no volume, and also have no molecular attraction, but real gases have this. So for our Van der Waal, what our Van der Waal is trying to correct is correction to volume, so that we can tell the volume of the gas, and also correction for the pressure, so that we can have molecular attraction between the molecules of gas. So that ends that about real gases and ideal gases. And with that, we've come to the end of this topic, talking about ideal gas equation. Do not forget, hit the subscribe button, and of course turn on the notification bell, and do endeavor to share with your peers. For myself and the entire team, it's bye for now.